Thank you for tuning in. I do apologize for missing Friday and Monday, being sick. It's been a nasty weekend and I didn't want to share it with you guys. But nonetheless, I want to make sure that you're up to date on the material as the final is coming up. And I I want to make sure everyone does well and that you guys can be successful. So I wanted to post this video with just some information that I would have covered the last couple of days so that we at least, it's not ideal compared to a live lecture, but at least it gives you the info and we can discuss it more when I'm back. Anyway, as far as the quiz goes, I did post it. I've graded it. I was going to give it back to you today. Uh, as far as the methodology went, most of you had a grasp of it from at the basic level up to fully understanding it. And so I will say that these are not easy problems. They are challenging. There will be one most likely on the final. So one of the consistent mistakes I saw, which I wanted to point out, and I encourage you to look through the solutions yourself, but is assuming that omega is zero and that you have no tangential acceleration. So in this example, you can see very well, and it's it's you saw the copy, but you could see that you're given initially that this has 3 radians per second and an alpha of 8 radians per second squared. So you know there's going to be a tangential and a normal acceleration to bar AB. And then that likely means that you're going to have one for CB and possibly CD. Now, you don't go that far to solve it, and I did solve the complete problem for you in the solution. I only asked you to find the acceleration and velocity of this bar AB, and then to set up the equations for that. Now, I'm not going to go through that whole thing here since it's already posted, but one of the things I noticed is that when you for one is I wanted you to write out each link individually. So for example, if we write out the link for AB, then really what we're saying in this with velocities, we're saying that the velocity of B equals the velocity of A, velocity of B relative to A. And because A is a fixed point, we know that that's essentially zero, and we know that they're equal to one another. Now, we've defined this as omega cross R. And so if we do a R B relative to A, we're really saying we want to go from A to B. And because we know the direction is going down, we can intuitively know that the velocity vector is just going to be down. And so we have 3 radians per second in the K negative crossed with 0.3 meters in the I. So the result is K cross I gives us a negative J or a 0.9 meters per second downward. And so that's easy, I think, enough to see. When we go on to the acceleration component, though, again, we're going to say acceleration of B equals acceleration of A plus AB relative to A. Again, that's zero. But this component here, we know to be alpha AB K crossed R B relative to A, if we write it out, and then plus, and actually I'll say minus because it's, remember that the true equation is plus omega cross R, right? But we in our special circumstances, we can shortcut it as minus omega squared times R B relative to A. Now, when we do this, this is not omega squared cross RB relative to A, because what some of you were doing is you were saying omega, which is a K, crossing with RB relative to A, which is an I, and you were getting a J, which that's not correct because it's not crossing at that point. You're distributing it. So what this gives you is not a J component, but actually an I component. And so your acceleration should really look like this. It should be negative 8K crossed with 0.3I, right? So that's really your alpha AB crossed with RB relative to A. So that gives you a value of negative 2.40J, right? And then that's going to be minus 3 squared times 0.3I, which gives us a minus 2.70I. And so the proper way to, and if you leave it like that, that's not the end of the world, but really you really want to write it as minus 2.70I minus 2.40J meters per second squared. That's the correct way. So again, this is a distribution, not a cross. So that's an important distinction. I saw it often enough that I felt it should be mentioned. The other thing is that you don't need to make this into a magnitude and an angle. Typically in this type of problem, you're going to leave it in this format because then the next step is to take this value here and form your equation for this. All right. And so that was one of the issues. The other issue was the drawing of each of the diagrams. Remember that whenever you're drawing each specific one, you want to acknowledge the accelerations. And because, for example, AB has an acceleration that's going to be down, right? The A tangential, it's also going to have A normal. Then therefore the bulk acceleration or the average is that. Okay. So if you did this or this or that was fine. So if you didn't, that's where the few points came off. But again, otherwise, if you don't understand this, be sure you do by the time the final comes. All right. This is very important. Review these problems, review the examples, because this is going to come back to see you. All right. Okay. Now I want to do another example from chapter 16, and then we'll move on to chapter 17. So here's the back side of the problem that we didn't get a chance to do. The crate is held, and then immediately after the man drops it to the right, the crate doesn't slip, but it starts to accelerate. And so we want to know what the acceleration is of the crate and the reaction. So this is similar in the approach to the problem we did with the 3 linkages that fell to the right that were connected, and we had to find the reaction forces. So let's draw it out and see what it looks like. So the first thing you want to do is go ahead and draw your MAD FBD. So I would recommend pausing the video at this point to do that, and then clicking start again after you have. The more you master this, the better you're going to be. So go ahead and pause and then resume when you're done. All right, so now you've resumed, and this is what it looks like. So you have mg, you have I alpha rotation, and then you have this part here is g, and then this is point E, it's pointing back to. And so I've kind of elaborated on that here. So really on the kinetic diagram, you really just have to have the 2. And this one here, the omega squared r, the normal acceleration, of course, we know it's going to be 0 because these are always instantaneous in time just as you release it. So there's no omega. So we can get rid of that term. So really we just have mr alpha, which is a MA, right? That's the same thing, only we use R alpha in this case. And again, that's very specialized only in 212. So if we look at this circle created based on the geometry, it's 0.5 high, so it's 0.25 up in this direction, and then 0.85 minus 0.6 gives us 0.25 in this direction. So we have a right triangle. That means that the distance from here to here, the hypotenuse is 0.354, or essentially you could use, using trig or Pythagorean theorem, whatever, you get 0.354. All right. So now again, this type of problem, we're going to sum the moments about E. And why E? Because we want to find the reaction at E, right? And so we want to get rid of those unknowns. because we have these two unknowns here. We have EX and EY. So let's get rid of those. And also because we're studying the moments about E, that's gonna be what it, and I'm gonna make clockwise positive in this case. So it's gonna be the center of gravity, IG, or commonly that same thing. So I could put IG or I can just put I bar. That means the moment of inertia about the centroid times alpha plus my MAD perpendicular. All right. So if I look at just my, which I know that acceleration, of course, is going to be R alpha, and my D perpendicular is just R bar. Okay. So when I go ahead, what are the moments about E? The only moment really is the weight. So I have an 80 kilograms times 9.81 times 0.25, right? So that's its distance. And then that is going to equal, now the one of the things I didn't do yet, it's all right up top. So let me pause for a second. So I left out the moment of inertia. So here's the moment of inertia. Again, you'll be given these equations, but one for a box, it's 1/12 m a squared plus b squared. So notice it doesn't matter which is which. So if we plug in the values for the width and height, we get 11.267 kilogram meter squared. So we come down here, plug that in again. So we have some of the moments about E, and then we have the moment of inertia times alpha, plus our additional moment created by the acceleration of the moment of the center of mass. So that's 80 times 0.354 alpha, that diagonal distance, times 0.354. So we calculate alpha gives us a 9.23 radian per second squared. And that's clockwise, given my convention. Makes sense, it's going clockwise, not counterclockwise. So because of the way I did the convention here, I came up with a positive number, and that's fine as long as you indicate which direction it's going in. So sometimes it's easier to just keep things positive. And a secondary thing on life, always be positive, right? So then for the reactions, just like we did before, we know that EX is just going to equal the result of the sum of the forces. So sum of the forces in the X equal MA in the X. So EX equals 80 times its acceleration, 9.23, times its distance, 0.354, right? So again, acceleration being combination of those two, and then cosine 45. And so that gives us a 184.7 newtons is our EX. And then Y is similar. The only difference with the Y is we also have gravity. So we have EY is equal to 80 plus 9.81. I'm sorry, not plus, times. So 80 times 9.1, so that's our mg. And then also we have to add to that the 80 times 9.23 times 0.354 times sine 45. So we know that this, of course, is just going to be 0.25, just like up here. This whole distance is 0.25 because that's how we got it in the first place. So it makes it a little easier. So again, reaction is just some of the forces in the Y, some of the forces in the X, pretty standard stuff. And so this gives you a value of about 969. So overall, you have a reaction that's about 79.2 degrees and a magnitude 987. All right, show you that a little closer. So mass times gravity plus mass times acceleration, right? And then times distance. And so And that's pretty much it. So there's something that's bugging me. I think there needs to be an extra value in there. Let me pause and check that for a sec. Never mind. I was thinking a moment. It's just a force. So since it's just a force, it's just MA. That's all it is. So those are correct. All right. So that's it for chapter 16. Let's start chapter 17 while my voice is still working. So chapter 17 is broken into two parts. There's 17.1, which talks about energy methods for rigid body. I think these will be very intuitive. I think energy overall has been probably one of the easier concepts to understand based on the feedback via grades on your part. And then 17.2 deals with momentum. So that's a little more challenging, but I think still, given the fact that we've covered this stuff in particles, I think the jump to rigid bodies isn't too difficult. We try to make our problems as simple as possible. So, I mean, in terms of our assumptions. So obviously things can get much more complicated, but we don't need to worry about that now. We're just looking at the basics. So remember that we looked at forces and accelerations. That was primarily what we did in chapter 16, right? We said the sum of the forces is equal to ma of the center of gravity, and then the sum of the moments about the center of gravity equal to the change in angular momentum. Now we're going to talk about work energy, which is energy added to the system, and then final energy. And then lastly, we'll deal with impulse momentum. So that's what we're going to have in the next few days. So this stuff is right out of your book, so I'm not going to spend a lot of time on it, but it just gives you kind of an idea of where we're coming from. So we know our system's made of a large number of particles, and we know the total work of the system has to be conserved. And so a good way to think about it, and we're not going to get into systems of particles, but we're really just looking at a rigid body. Now, the big difference between rigid bodies, and you can read this on your own, but it comes from the fact that now we have rotation that we're dealing with. So you may recall with energy before, whenever we had motion, it was single or motion in terms of just particle motion. So we'd have our 1/2 mv squared to indicate velocity, but we didn't have any kind of a rotation in there. So we had no what we call 1/2 I omega squared type energy. So where does that come from? Well, one of them is this. And so what I'm going to do is let me stop to share. Well, actually, I could just point it out, but really what the basis of this is saying that you recall that force times distance was energy. So when we did our U1 to 2, let me pause this. Where's that? So when we did you remember that when we had force times distance, that was our energy, right? So usually that was going to be a force applied, or we also commonly looked at it as friction. So the same thing can be said for rotation. And so if we have a moment, right? So there's a force applied, and then there's our rotation. So force FR, that's our moment. And then if we say, okay, this thing goes around pi, then that's our theta. So what we end up with then is in that case, if we're looking at the energy involved with that, we would say 1/2 I omega squared. Say it's a particle moving around a circle. That might be our T1. And then plus our moment times theta. And that's our U1 to 2. And that is going to equal our 1/2 I omega final. So we'll say that's initial, that's final squared. So just as you can picture something going around a circle, if I add a moment and a force, how to say, a force times distance or a moment over a certain amount of angular radians or number of radians, then that's going to increase it. So this is no different than 1/2 mv squared plus force times distance equals initial equals 1/2 mv squared final. So same exact thing. It's just difference in rotation. That's all it is. So, I mean, you can look at the theory if you want and or how it's derived, but I think it's pretty straightforward. So going back to this, we can look at it also, and this is where this comes from. If you have if you have several things in a system you have to account for, which means that if you have a body that's both rotating and translating, then you have to combine both of them. And so what this final thing, T, is saying that you account for the rigid body's motion, the center of gravity's motion as 1/2 mv squared, where v bar is the motion of the center of gravity. And you also account for the 1/2 I omega squared. And so we're going to treat these as independent. So our problems are going to have a fixed axis of rotation, and they won't generally have, if there is motion, it'll be something that's maybe attached to the object. So we're not going to do translating axes, so don't worry. All right, and that's just what I said here. And there's our actual equation, just like I said. So I would just, pause this, write it down, understand it. I'll go over it, or I'll reiterate it in class, but this is essentially all the additional information that we have in this chapter for this topic. Okay, here's a theoretical question asking if you have a slope and you have these objects, a solid sphere, a solid cylinder, and a hoop, all with the same mass, which one's going to go the farthest? So intuitively, if they're the same, if it was particles, then of course we'd say it wouldn't matter. But since we have moment of inertia or mass moment of inertia, that's going to determine, and that's going to be the resistance to rotation. So what we do in this case is we look at what are the mass moments of inertia for each one. So it turns out that for a sphere, it's going to be equal to, so I of sphere equals 2/5 mr squared. And for a cylinder, it's 1/2 mr squared. And for a hoop, it's just mr squared. So if they all weigh the same amount, then this one's going to have the lowest I. So this one's going to go the farthest, the sphere. Okay. Now, if we look at the second problem, I don't know why they call them problems. They should be called exercises. But in this case, you have a solid, an object rolling down. So I should do a better job of having an object rolling down. But what that is saying is, if, let's just draw it out. So here's our diagram. So we have this here, and then we have this here, basically rolling down. And so 2m, m. And so which one's going to have, the more velocity, go farther, whatever. So we know, though, that when we look at the equations, we usually look at what height. And so we know that if there's no friction, nothing else, we know it's going to be 1/2 mv squared equals mgh. And so notice that whenever we look at that, we know velocity is just equal to 2gh. So since there's no mass in that, it's independent. So both of them, and if it's smooth, would fall or get there at the same point. Just like if we were to drop, two objects in a vacuum, feather and a hammer on the moon, and they both reach the ground at the same time. Sorry, I have a little bit of coughing there. Um, so let's share again and see if I can. So I'd like to look at this example here. All right, so here you have a 12 kilogram slender rod. Well, you can read it. So go ahead and read it and then try to draw what you think the condition is going to be um, before and after. So it's not really it's because we're not in F equals MA, it's going to be kind of what it looks like before, what it looks like after. So if you can visualize that, then you'll be ahead of the game. So go ahead and do that, and then I'll draw it for you, and then you can compare. So go ahead and pause. So here's what our diagram looks like initially. So we have the spring stretched, and we know that that's 30 degrees given. It's 2 meters long, 150 degrees. We know it's 12 kilograms. So if we look at this the way it's written, we know if that's 150 degrees there, then that's 2 meters, that's 2 meters. We know the stretch, so we can use the Pythagorean or law of cosine, sorry, to find the distance BC. So now we know it's stretched at this location in space, it's stretched 3.864. And we're given that its relaxed state is 2. So we know that it has a stretch of 1.864 meters. Of course, that's important because that's going to give us the elastic potential energy that's involved. Okay? So now if we draw out what it looks like before and after, it looks like this. So here's our new diagram, right? So we have, this is our starting position here, and here's our ending position here. Now we know that because the ending position is going to be such that this spring is going to be a total of 2, right? Now we know that this is 2 also. So my drawing is not perfect, but we know that this is going to be an equilateral triangle based on geometry. So therefore, this angle here, 60. And so in this case, we have kinetic potential energy, and we also have gravitational because the center of gravity is going to shift, right? Because if this is 30 degrees here, we know this height is just going to be 1 meter because the opposite side of that triangle. Whereas we know this is going to be about 1.7 or so based on that. So what we wanted to, we know that our delta y is equal to 0 point, actually, I'm sorry, not y is 1, it's half actually, yeah, because the center. So the center, so this thing is 1, so this is going to be 0 0.5. So let me write that. Still same idea, it's just I doubled my values. So if that's 1 and that's 1, then this y1 is 0 0.5. This y2 over here is going to be just 0 0.866. So the delta is going to be equal to 0 0.366. So that's the change in height. All right. So now because it's a rigid body and we're given it weighs 12 kilograms, which is kind of convenient because we know that I of the rod is going to be equal to 1/12 times 12 times L squared. Okay. And so that's 2 squared. But we're not rotating about the center, are we? Because that would be if we were rotating about this point, but we're actually rotating about the end. So we have to use parallaxis theorem. We have to add to that the MRD term, which is going to be 12 kilograms times this distance, which is 1 squared. So that gives us a total of 16. Nice even number, kilogram meter squared. Okay. So now we know that our object's going to be moving, right? So it starts at rest. So we can write T1 plus U1 to 2 equals T2, right? So nothing's changed, even though rigid bodies, gravity, or I'm sorry, energy problems are still the same. So for 1 is we know that our initial, we'll say, amount, or our initial t is going to be 0, and our t after it motion, the t2. So we'll say let's break it into two components. I think that'll be easier. So this is the t. Actually, I want to do this a little different. Let's rewind and pretend you didn't write this. So we know we have that, okay? And so our overall equation is going to be what? It's going to be T1 plus V1 gravitational plus V1 elastic. And that's going to equal T2 plus V1 gravitational, and then plus V2 elastic. So instead of using the shortened version, I'm going to use the longer version. And that's because I have both gravity and elastic. So my T, though, in this case, this is kinetic energy, but we don't have any translation, we only have rotation. So my T2 is going to equal 1/2 I omega squared. So in this case, it's going to be equal to 8 omega squared, right? Because this was 16. So you can see that. T1 is 0. I'm going to say that my initial gravity is going to be also 0. That's going to be my datum up here. And then, so I'm going to have to then subtract that off when it goes to the other side, because that's going to be added value to it. So if I go ahead and I set this up, what do I have? I have 0 plus, now first off, I have my 1/2 40 times 1.864 squared. So that represents my elastic. That's my kx squared, remember, because I have a distance of 3.864 minus 2. So that was the distance I showed earlier. And so there's that. And then I have to subtract off the motion. And so I guess one way to do it is you leave the gravitational in for both sides, or you can get rid of it. And so maybe to show the gravity, you can also put it in as add them together. So what I'm going to do instead is I'm just going to say this plus, and I'm going to move this over here. So it's basically going to be the difference. This is 0 because it's relaxed. So it's going to be the difference of gravitational. So it's going to be the 12 kilograms times 9.81, and then times just the delta, which is 0.366. And then that all is going to equal my 8 omega squared. And that's it. All right. So I think it's easy to understand. You have the rotation. So you have some kinetic energy stored in the spring. I should say elastic energy stored in the spring. You're not moving. You release it. It swings over here. So you have the energy of the spring converted to omega. You also have that little bit of difference in height converted, which is just this. And then all of that is added to the final result. So if we solve, we get omega equal to 3.75 radians per second. Sorry, I was a little longer than it should have been, but I hope that makes sense. I think that's a good introduction problem to this concept that if you read it and understand it, you should be in pretty good shape. All right. Okay, well, I think that's a good point. That's about as much as I can talk right now. So I will drag myself in on Wednesday, come hell or high water, but hopefully that will help you. So I look forward to seeing you, and have a good evening.